of the session, Till Hauser will tell us about entropy beyond actions of uniform lattices.
Thank you for the nice introduction. Also, thanks to the organizers for giving us the opportunity to finally meet in person once more. I really enjoy this here. Okay, so, what is entropy beyond actions of uniform lattices? So actually, what I want to talk today about is basically entropy theory for actions of groups which are not necessarily discrete. And I framed it like this. We will see it in the talk. So basically for actions of non-discrete groups. And I think it's best to start with the known context, the context of actions of discrete groups. So let's start with a discrete amenable group. So an amenable group is simply a group which, if it acts continuously on a compact Hauser space, we will always have an invariant regular Borel probability measure. And this kind of characterizes the amenable group. But now we want to go into the context of measurable systems. So we want to talk about measure preserving actions on some probability space X mu. And just as a reminder, here's also the definition, but I assume that most of you are familiar with these kind of definitions. In order to define entropy in this context, we will need some averaging tool. And this averaging tool is actually, for example, here I will use the Pöllner net. If you don't like working with nets, you can also work with sequences. Then you need some countability assumption on the group. For example, you need a discrete countable group. This kind of Pöllner net here, I guess, is the abstract definition. So it's some kind of invariance property. It becomes more and more invariant. But I assume it's best to start with an example. So I guess this is the most famous example of Pöllner sequence, which is used in the Birkhoff-Ergodic theorem and so on. And I assume it gives already a good intuition for the Pöllner sequences. For discrete groups, one can use these Pöllner nets in order to characterize the amenability. So amenability is equivalent to the existence of such a net. And then this is why I chose this context in order to define the measure theoretical entropy. One uses these Pöllner nets in a very similar way to the standard Kolmogorov-Sinai entropy. And also, instead of Fekete lemma, one has other subadditivity tools, but all goes in a very similar manner. And this is basically the definition how to define the entropy of such an action of such a discrete group. Down here are some more of the definitions. So, for example, one has the Shannon entropy, H alpha, just to give a bit more of the notation here. And alpha lower F shall mean some common refinement of alpha, basically shifted copies of the finite partition alpha, and then the common refinement. Okay, so this is basically stuff well known and the well-studied context, but I'm also interested in aperiodic order, and there one quite naturally encounters actions of non-discrete groups. So this is why I want to go to the more general setting and get rid of the discreteness somehow. I want to study actions of general amenable groups. So let's choose. Again, it's defined by the existence of regular invariant Borel probability measures as soon as this group acts on compact Hauser spaces continuously. And again, also here, one can define what a measure preserving action shall mean. We do it as before, but we want also somehow include the topology of the group, right? So somehow the topology of the group should connect with this action, and we do it with these three here, this continuity condition kind of. And on the first slide, it might seem quite strong, but it actually isn't. So due to a result of Ornstein and Weiss from 87 in their famous entropy paper. So for example, if the group is locally compact, then actually whenever G times X to X, so this map is measurable, which is a very natural assumption in this context. then one already obtains discrete. And now the question is how to define the entropy of such a measure preserving action here. And the big problem comes from the alpha lower a, so which is just notation right now, but really one wants to define it properly. So in the discrete context, the lower a was some finite set, right? Fellner sets or Fellner nets, they consist of finite sets. So doing some common refinement with respect to finitely many shifts of our finite partition, that makes a lot of sense, and we get a finite measurable partition once more, and everything's fine. But here, generalizing Fellner nets basically leads in different directions, but the most common of these generalizations, they consist of compact subsets. And alpha lower a with respect to a compact set A just does not make a lot of sense, because it would mean shifting by a lot of, basically infinitely many points in A. And then just the common refinement makes no real sense. So one has to think about some way to go around. And one way to go around this is just to say, okay, I don't want to talk about the amenable group. I just consider a certain discrete subgroup and then talk about this. So this is what is, for example, done if one considers flows of the reals. Then one says, okay, let's just talk about the respective action of the integers. And one obtains that there's a nice entropy theory. We use this, we compute the entropy like this, and everything works out fine. So this is a good idea. And this clearly also works more general. So what is a good generalization of the integers inside the reals? It's this notion of the uniform lattice. So it's a discrete subgroup such that the quotient is actually complex. And then what one does is, okay, then one considers the respective action of this uniform lattice, and one can actually compute the entropy. One has a lot of entropy theory already developed for this, and everything is nice. But there's one big problem. And the big problem is that there are a lot of groups which just simply do not have such a uniform lattice inside. An example is the additive group of p-adic numbers, which is a very nice group. So it's metrizable, sigma compact, locally compact, abelian. So it's a very nice group in a lot of senses. But it just has no other than the trivial group, a discrete subgroup sitting inside. So one cannot do such a trick for such a group. And therefore, and this was just my introduction, therefore I want to consider two more ideas, so idea 2 and idea 3 today. And we will see the second idea, which I call Onshore Entropy. It's kind of a dead end, but still I want to present it today. And we will see a third idea that I call Onshore Entropy, because it goes back to techniques developed by Ornstein and Weiss. And this one will actually be a good generalization of idea 1. And at the end, I want to finish with also some topological remarks, so one can also develop in a similar manner a topological entropy theory. Okay, so let's start with the dead end thingy, with the Onshore entropy. So we consider some general amenable group, and we use so-called thin Fellner nets. So thin Fellner nets, what is it? I will define it in a second, but it is, first of all, a generalization of the Fellner nets from the discrete context. And here comes the definition, which is a bit technical. So basically, the big advantage here, and this is why I underlined it, is that these thin Fellner nets, they consist of finite subsets of the group. I think it's the only generalization of Fellner nets that I know of, which does not consist of compact subsets, but of finite subsets. So one can use this, for example, in order to make the Krylov-Bogoliubov theorem run and a lot of such things. So it's a nice generalization. So it's not just something weird. Okay, so how does it work? Maybe it's best to draw a picture. So let us take, for example, the black dots there. And let's say this is one of these Fellner sets. And these crosses are a shifted copy of it. Basically, what we want is we test it for parameters, which is, for example, the size of a ball or some open neighborhood V here. And basically, we want that it matches more and more the longer we wait. And asymptotically, it basically becomes invariant, but up to some wiggling. And the nice thing about these Fellner nets as well is that actually in the non-discrete context, as in the discrete context, basically the existence of a thin kernel net again characterizes amenability. So assuming a general topological amenable group, not necessarily locally compact, for example, one can again characterize amenability by the existence of such a thin kernel net. Here's some examples just to put some illustration behind this. So this has two components, kind of this example. So first of all, one sees more and more of the space by this growing interval 0 to n, not necessarily the whole space, but more and more. And then also one gets kind of denser and denser, which is given by the first part of the case. Okay, so this is an example. And now I can use these thin kernel nets in order to define entropy once more, similarly to the definition given by Kolmogorov in C9. And so basically what one has to discuss here are two things. First of all, does this limit again exist? So one needs again some subadditivity argument. And the second thing is, does it depend on the choice of such a kernel? And this is a theorem given by Friedrich-Schiller-University Schneider and me. And it is about basically that both works nicely. So it's independent from the choice and the limit exists. And the arguments are very much similar to the arguments given by Jean-Moulin Olanier in his work. So we kind of generalize techniques of him. So what he uses is some sort of subadditivity. It's even stronger, works in the measure theoretical context, called strongly subadditivity, and also right invariance of the map given up here. And I don't want to put this precise, but if you have questions, then keep ask. What we also need here, because we are not in the discrete context anymore, now we are in the more general context. So we kind of have to explore the topology of the group. And we do this by putting some topology on the set of all finite subsets of G, which I denote by f of G, and then basically also using the continuity of the map given there. And using this as well, one can basically make the Olanier theorems run and then get this result. Actually, this yields a little bit more, which leads to the definition of naive entropy. And basically, instead of the limit, one can also put an infimum there, which is well known from the Piquet lemma, for example. So it is very nice in the context of the integers, and one can even like push it up to this level. And so the proof, which is sketched here, actually also yields that the naive entropy equals the Olanier entropy. So this is something which we also get, but which is also kind of unfortunate, which I want to present next. So first of all, please realize that naive entropy can be defined in a very general manner, and actually given for actions which are not even groups which are not even amenable, but just some general topological group. Okay, so using this definition, we have the following theorem, which is that whenever oh, sure. Yeah. Test. Does it work? Test. Yeah. Okay, so let's come back to naive entropy and the bad news. So the bad news is that whenever my group is metrizable or locally compact, so one of the conditions is enough to screw everything up, then it suffices to consider non-discrete groups, and you will always have naive entropy 0. So this is kind of bad for us because then it equals the Orlanier entropy, and my notion of Orlanier entropy is just not worth talking about it. It's always 0 in the context of the groups that I'm interested in, the locally compact one. So this here's a short sketch of the group. So what one does is one uses some sort of algebra isomorphism and basically a topological model. The topological model is not necessarily uniquely ergodic, so the original action is not necessarily ergodic as well. So one can do this stuff for general measure preserving actions, and basically what also the isomorphism is on the measure algebra level. So it's on a kind of another category thing. And basically what one does, one constructs a compact Hauser space, which then gives the topological model. And basically using the topology, one can also talk about naive topological entropy, show that the naive topological entropy is 0. And then we use a result by Peter Burton that naive topological entropy bounds naive measure theoretical entropy, and therefore obtain, okay, so the naive measure theoretical entropy has to be 0. Okay, so bad news. Let's go to idea number 2. So let's talk about the Ornstein-Weiss entropy. And here we have to restrict our context. So we can't, at least I don't know how to do it. We can't talk about general amenable groups, but we will restrict to the context of unimodular groups, which are given. So the group is a locally compact group. Therefore, it has a Haar measure. And if the Haar measure is not only left invariant, but also right invariant, then we call the group unimodular, which is even more restrictive than locally compact. And in this context of unimodular amenable groups, we will work them. And now we want to use Van Hove sequences on that for averaging, which, here's the definition of the Van Hove boundary, but I guess it's best to draw a picture. So let's consider a set A and basically some scale K on which we want to define the K boundary of A now. And it's done as follows. So we blow up A on the scale of K. We do the same with the closure of the complement of A. We obtain that basically this intersection, this is the K boundary of A. And net of compact subsets is called a Van Hove net if basically with respect to the Haar measure, this boundary vanishes with respect to the full set for any choice of such a parameter K, a compact subset. Okay. And again, in the context of unimodular groups, this characterizes amenability. So we will always have a Van Hove net in our context here to work with and to do our definitions. Also, this stuff generalizes again the Fellner method from the discrete context. And here are some examples. So for example, in RD, which is such a group, we can use the balls of radius n or the cubes. Here's a more exotic one in R. So it doesn't have to be centered or anything. It's the space where these objects are doesn't really matter. And also in the p-adic numbers, we have such a Van Hove sequence. We can also just use the ball. And I need another ingredient, right? I already talked about that we cannot just use compact subsets in order to do this kind of common refinement. So we will need another ingredient, which is given by the so-called Delonata set. And the Delonata set is a discrete subset, which is even more than just discrete, it's uniformly discrete. So we have an open neighborhood V of the unit, and basically shifting this to all the points of the discrete subset, we get basically a disjoint family. It is also relatively dense. So we have a compact subset, and shifting this one around will give us basically a covering of the whole group. And if it has both properties, then we call it the Delonata. So here are some examples. So the integers inside the reals, they form a Delonata set. Also this n plus 1 over n, where n is a non-zero integer, also this set is a Delonata. And here now come the important observations. So first of all, a uniform lattice is nothing but a Delonata subgroup. And the second observation is, I mean, we already know, for example, the p-adic numbers they don't have a uniform lattice inside. But any locally compact group always contains a Delonay subset. Not a subgroup, but a subset. So basically the idea is now to kind of, instead of using the uniform lattice inside, we use the Delonay subgroup inside. We use just the Delonay subset inside it for our averaging. And we do this because intersecting basically a Delonay set with a compact set always yields a finite set, and we can use this for our average. Okay, and okay, here now I just summarize all the setting that we had. So we are in a unimodular amenable group, we have a Haar measure, we have our measure preserving action, we choose a Van Hoven net, and we choose the Delonay set, and we define the Onstein-Weiss entropy as follows. So again, we have the supremum over all finite partitions, measurable partitions. Here we have the lim sup. We don't know whether it's a limit. I don't think so. And basically what we do, we use a very similar definition than given by Kolmogorov in Sinai. And basically now we have alpha lower, and there we need a finite set, which does AI intercepted everything. Okay, and here two questions naturally arise. Does the one question. So first, the question which I kind of answered already is, does the limit lim sup, is it a limit? Well, I don't really know this, but I don't think so. The second important question is, does the stuff depend on the Van Hoven net? Does it depend on the Delonay? And this is a theorem by us. It does not. So this is actually this. It's a nice way of computing it, and you have a lot of freedom to choose these objects. But at the very end, this supremum does not any longer depend on these objects. And here's the sketch of the proof. So again, one chooses a topological model. Then one uses the uniformity, or if you like, a metric, if you want to be a bit more restrictive with the context, but one uses the uniformity and the context of general complex Hauser spaces in order to define another approach to this notion, which does not any longer depend on omega, but on AI. And then one uses subadditivity arguments developed by Onstein, Weiss, and Gromov in order to basically make this stuff run and show the independence of the AI. And then kind of gluing everything together, one obtains the independence from omega and the Van Hoven. And a nice corollary of this stuff is now, because if G contains a uniform lattice, then one can just use this uniform lattice instead of omega. And we obtain basically the standard notion of entropy, our idea one, and just see that this is just the same as idea one as soon as I have a uniform lattice. And yeah, up to some rescaling of beta. I mean, this depends basically what the fundamental domain of my uniform lattice, if you're familiar with this notion, so beta, what the Haar measure of this quotient basically. It is just up to some rescaling of my beta. Okay, and here's some other example, which is, I guess, interesting for a lot of you because you are more interested into actions of the integer. So if I take basically a Delonay set inside the integer, then this stuff is still interesting because it kind of means that I can kick out information randomly and still compute entropy as long as I have basically a boundary on how much information I kick out until I know something again. And this is given by this formula. So still this kind of formula gives something in the context of the integer. Okay, and as I promised at the end of my talk, I want to talk about the topological side of the whole entropy theory. And okay, again, I guess known by Konheim and Adler, the following definition is quite like, if you've seen the previous one, then this one, writing down this one is just natural. And again, one has to ask the question whether this stuff depends on the choice of the Van Hoven net and the Delonay set. And again, it does not, with similar techniques. This time, we don't even have to choose the topological model because we are already in the topological context. And therefore, one basically uses similar theorems, similar arguments. Again, the Onshore and Weiss technique. A theorem that we also kind of discovered talking about all this stuff is, I mean, it's a very natural question to ask for the variation of principle now, right? And so we could only show one side in this generality for general unimodular amenable groups, which is the one given here. It's basically the Goodwin direction, and basically that the supremum over all mu of the left-hand side, the full variation principle, that this is equal to the right-hand side. We can show this in the abelian context, which was enough for me because I wanted to use it in this aperiodic order context, but it's still kind of open how to do the full variation. And also a remark, so basically all this stuff that I showed you about topological entropy, we also did in the context of topological pressure. It's not so hard to kind of generalize it in this direction. I just didn't want to present it here in order not to put too much information into this. So, okay, then I wish to thank you for your attention. And if you have any questions, then please ask. Thank you.
Okay, you were invited to ask questions. Do you have any? Yes.
Simple question. Do you have any applications in mind for this entropy theory once you classification or something?
So it's basically what we were talking about, what we were thinking about is in the context of aperiodic order. So the notion of Delonata set that I defined in this context also appears in this aperiodic order context, where one also considers kind of special cases of this Delonata set. And then one basically uses the Delonata set, shifts it around in space. So one has basically a lot of shifted copies. And then this set of Delonata sets, I mean, you have a topology on this space. And then one can close it. So one obtains a compact Hauser space, where the points basically are these Delonata sets. And then one can act on this by the group. And then this naturally leads into the direction of basically actions of non-discrete groups. For example, of the p-adic numbers, because one can do the very same stuff with Delonata subsets of the p-adic numbers. And what I also considered, and this is some other paper, some other work, and is that one can, for example, look at the shift space, right? And one can consider some board counting entropy there, and one can do a very similar thing with the p-adic numbers. But the problem there is that actually in the usual context, for example, for the reals or the integers and so on, the topological entropy equals these counting entropy. And for the p-adic numbers, this is not any longer the case. It kind of breaks out. And this is why I wanted to have a proper entropy theory in my bag in order to do everything right.
Yes. Okay, any more questions or comments? If not, then let us thank the speaker again.